Hey there and welcome back. This is the third video that I'm making in a series of videos over rate of change and how we're going to apply them to a calculus situation. So here, the example in your notes is we want to be able to take the heart rate and see what would be the rate of change over a person's heart rate from one time interval to the other. So here, reading the question, we have a person that's been exercising, which is great. Always good to get your heart rate up. Where they're saying we have a function h of t, that's going to represent your heart rate. Now, we're not interested in really what the function actually looks like. We just want to be able to write an expression for the rate of change of the heart rate over a period of time from 0 seconds to 90 seconds. So here we're trying to see what would the expression be that we could substitute some numbers in if I actually wanted to know what the rate of change was. We don't want to know what the actual rate of change is, but what's the expression that we would use for this scenario. So go ahead and take a second, pause the video and see what you come up with, and when you're ready, hit play again so you can compare your work with mine, and then we'll move on. All right, so looking at the function here, we're talking about rate of change. So just like with slope or the leaning tower Pisa problem that we saw in example 1, we're looking at the change of some dependent variable numbers with the in a ratio with the change in the independent variable numbers. Well, time is the independent variable, so I'm going to say something with delta h, the heart rate, over delta t for time. And in this case, it will be somewhere, I have it typed, there we go. The time interval from 90 seconds to 0 seconds, we'll take the difference of that. Now, if you wrote it in the other order, if you said h of 0 minus h of 90 and 0 minus 90 in the denominator, it would be the same value when you simplified it. And the difference between the answer on the left and the answer on the right, between 90 minus 0 or the 90, either of those would be considered correct because you don't need to simplify your responses in a free response question. That would be the expression for the rate of change of the person's heart rate from 0 seconds to 90 seconds. We're not asked to find what the actual rate of change is, just what the expression would be for it, and that's how we do it. Now moving on to the next example, we see we're talking about a roller coaster where the drop in the roller coaster is modeled by the polynomial expression below, d of t. Now this is very similar to the leaning tower Pisa problem that you saw in example 1, where we want to know, in this case, in part A, it says what's the average rate of, or average speed of the roller coaster over the time interval from 2 seconds to 8 seconds. So we're still talking about a rate of change, meaning that we need to identify what are the output numbers at 8 seconds and 2 seconds, so we can take the difference of those in the numerator, and then we can take the difference of the time in the denominator and write our solutions there. And then here we go, there it is. So the delta d over delta t, I'm going to substitute 8 and 2 into the given function, and I'm going to get about 671 and 290 or so for the corresponding output numbers. Now, keep in mind, these numbers may be rounded when you write them on your paper, but for any calculations that you do with these, you don't do any calculations with rounded numbers. You save them in your calculator somewhere so that way you can continue using them. Taking the difference of the numerator, we get about 380.8 in the numerator divided by 6, and we say the average rate of change along 2 to 8 second time interval is about 63.47 feet per second. Okay, so moving on here, see if you can go ahead and pause the video and try working out example B here, because this is the same concept, it's just over a different time interval. So go ahead and pause the video, and when you're done, hit play and come back and see how you did. Okay. So the average speed here is going to be from 4 seconds to 6 seconds. So I still have to know what are the output numbers, what are the y numbers at 4 and 6 seconds. So I'm going to substitute 4 and 6 into the given polynomial, and I get about 470 and about 373 for the 6 seconds and 4 seconds. Taking the difference of those, I get about 97.02, and I divide that by 2, and so I'd say the average rate of change from 4 to 6 seconds is about 48.51 feet per second. Now, those are average rates of change along a specific time interval. We want to know what is the instantaneous rate of change at exactly 5 seconds. Now the table that I have in the presentation here just has those 3 time intervals on it, which is fine. That's really all you need, I guess. But the table that you have in your notes is a little bit different. So using the third degree polynomial, the d of t function that we saw, evaluating it for the specific times that you have in your notes, we get the corresponding output numbers. So moving down, where it actually says explain the meaning of the instantaneous rate of speed in context of time is equal to 5 seconds, we need to approximate it. So here, somewhere, there we go. The instantaneous rate of change, I'm using 5.0001 seconds as my time interval, so 5.001 to 5. And when I plug those numbers into the function, I get about the 414.3 and the 414.26. And when I take the difference of those and divide it by the 0.0001, I get about 46.641 feet per second. So that's how we can, if we close that time interval in the denominator to get closer and closer and closer to 0, we can see how we would approximate an instantaneous rate of change at a specific time. So that is, this is going to be the end of the third video, and we're going to do one more for example 4 that we see in our notes. But if you have any questions about anything you saw here, please just let me know. But until then, until we talk again later, thanks for watching.